All right, good day, everyone. Welcome to this exciting episode of our YouTube lessons. I'll be looking at a simple reaction that has to do with dehydrogenation, or rather dehydration of alkanols to produce alkenes. Okay. Let's say we have an alkanol like this. Let's say I have an alkanol like this. I have CH3, and I have CH3. Just watch. Okay, I have OH. I have CH3. Okay. I have an alkanol like this, and I'm about to dehydrate. Okay. Alkanols are mainly dehydrated in presence of H2SO4 or mineral acid as catalyst. All right. With ethyl hydrogen tetraoxosulfate 6 as the or alkyl hydrogen tetraoxosulfate 6 as the intermediate. Okay, but I'll focus on the principle of the reaction and how it works and some basic rules that are governing, such as the SAYTZEFF rule, which was proposed by Alexander Zaitsev, a Russian scientist in 1875. Okay, now for this reaction, it's very simple. Now, if this is an alkanol, this is actually a tertiary alkanol, which is 2-methyl propan 2 or 2-methyl 2 propanol. Okay, if I'm to dehydrate this guy, what normally happens is that from the mechanism, the carbocation will be formed. So a carbocation is a carbon that is positive. So the acid will expel the base. So the acid will remove the base or the OH as from the I have a carbocation. So what I'm trying to say is that I have a carbocation intermediate. Okay, the intermediate of this reaction should be something like CH3, C. Okay, we have plus CH3, CH3. So the acid remove the base. Okay, further, the acid is going to attack the alkyl group to expel or to export or to remove a proton, expulsion of a proton. So it's going to remove an adjacent proton. So if it remove the OH here, it's going to remove a proton of any of the adjacent carbon, any of the adjacent carbon. So I will give you rules that governs when when which of the carbon will be gotten or which of the carbon will be losing the hydrogen. So, but now any of the adjacent carbon can lose hydrogen. So let's say we lose from here, and so we lose H from here. So then we're going to have. So if you lose H from there, I'm going to have CH3, C. Then up I have CH3. Then I have losing H. Then makes there create a double bond, and I have a CH2. So this is an eliminated product. So therefore, my product is going to be CH3, C, CH3, double bond, CH2. These are now alkene. So this was an alkanol. If you check, pause the video if you don't understand. I have an alkene. All right. So basically, alkanols are dehydrated to alkenes. This is an example of a reaction we call elimination reaction. Remember, this reaction just is a two-step reaction. Many call it an E1 reaction, molecular elimination reaction, and it occurs in two steps. It's a first-order reaction. First, the acid remove the base, creating a carbocation, which is the first step of the reaction. Second step of the reaction involve when the acid or the base form now export a proton or remove a proton from the adjacent carbon. So that's how it is. So basically, when you remove a proton from the adjacent carbon, any here or here, form an alkene. So that's simple dehydration. Okay, now there's a rule governing this is dehydration. What I just explained is dehydration. So if you are following me, dehydration is actually a elimination reaction. So there's a rule governing. There are rules governing elimination reaction. Okay, so I would like to talk about just two of them. And the first one I talked about kind of is Zaitsev. Zaitsev rule. Zaitsev rule. Some say Zaitsev. Yes, Zaitsev. Zaitsev. Yeah, some say Zaitsev. Okay, Zaitsev rule. Yeah, or I think this is it. But that's it's a Russian name, so it's not. I speak English, so I'm not into Russian, so I'm not into the name. So some say Zaitsev. Yes, Zaitsev rule. Now this guy Alexander Zaitsev in 1875 proposed a rule, and the rule states that now follow me because this rule will guide all our elimination. And don't forget alkenes. If you are learning how to prepare alkenes in subsequent in our videos, you see them how to prepare alkenes. alkenes preparation are usually from elimination reaction. The halogenation, you always see the halogenation, dehydrohalogenation, even dehydrogenation. So yeah, we're looking at dehydration because we are losing water. We are losing water. OH from the alcohol carbon or the tertiary carbon, and then H from an adjacent carbon. Remember, water consists of H plus and OH. Yes. All right. So SAYTZEFF rule is essentially an eliminated rule, is an elimination reaction rule used in organic chemistry. Now, SAYTZEFF observed something conventionally from its organic chemistry reaction back then in Russia. SAYTZEFF observed that during elimination reaction, this is what they observed. During elimination reaction, the most stable alkene, the most stable alkene, the most stable alkene is usually formed. So he said during elimination reaction, the most stable alkene is usually produced. So the alkene produced is usually the most stable alkene. And this most stable alkene is the most substituted. Yes, is the most substituted. So usually the most substituted alkene, that means the alkene with more alkyl substituents, or rather the alkene with more substituent is the alkene form. So the alkene form is alkenes with more substituents, is alkenes with the most substituents or the most alkyl group. They're the alkenes with the most substituent or most alkyl group. Okay, he said alkenes form are the alkenes with the most alkyl group or alkenes with the most substituents. Yes, and don't forget, these alkenes with the most substituent during elimination are usually the most stable alkene. SAYTZEFF said during elimination reaction, the most stable alkenes are formed, and the most stable alkenes are the most substituted alkenes. Okay, the most substituted alkenes are the alkenes with the most substituents or with the most alkyl groups. So I'm going to try two examples, and I think you can try others, practice others with yourself. Then I'll talk about dehalogenation and I'll talk about dehydrohalogenation. Simple. Now quickly, let me look at two. So if you watch, okay, let me just quickly look at two. Look at two to obey SAYTZEFF rule. So let me watch two. Let's just look at two reactions. Two reactions and see two. You might be laughing in your house now. What's two? Okay, two reactions. So let me look at two reactions. So mind you, this is SAYTZEFF rule. That is SAYTZEFF rule. Okay. I'll quickly like to look at two reactions. Okay, and I would like my left part of the board since it's okay, very okay for me to use. All right. So for my left part of the board, let me do a reaction here. Let's say CH3, CH2, C, COH, then I have CH3. Yes. So this is butan 2-O. Yes, that is butan 2-O. Now I'm about to carry out, for if you are following, we're about to carry out dehydration in the presence of a mineral acid catalyst. So what alkenes will be produced? So we are going to follow SAYTZEFF rule strictly. And remember, I was going to talk about two rules. SAYTZEFF rule is one of the rules, while the direct opposite of SAYTZEFF rule is the Hofmann's rule. So before I give you the product, the Hofmann's rule is the direct opposite of the SAYTZEFF rule. What did the Hofmann's rule state? The Hofmann's rule said this time, according to the Hofmann's rule, now the most stable alkene, according to the Hofmann's rule, take it somewhere, the most stable alkene is actually, listen up, the most stable alkene is actually the alkene that is least substituted. That means it is the alkene with the less amount of alkyl group or the less amount of substituents, which is directly opposite to the SAYTZEFF rule. Somehow Hofmann's rule came first in history. SAYTZEFF rule was later in the 19th century. So though Hofmann's rule was already in the early 19th century. All right. So it is their direct opposite. So normally, according to them, and today in organic chemistry, before I talk about them, the SAYTZEFF is widely more accepted than the Optimal's rule, and it has been proven several times to be more accurate than the Optimal's rule. So they are direct opposites. So in your exams, in your exam condition, you should not always follow Optimal's rule. SAYTZEFF rule all the way. SAYTZEFF rule is the rule that governs elimination, either E1 elimination or E2 elimination. So quickly, I have butan 2 or, okay, I have butan 2 or, and how do I quickly get the product? So I'll give you two products. So I'll write the original product and write what we might call the minor product. Okay, so quickly, I'll quickly do this. Okay, let's quickly watch. H2SO4 butan 2 or, butan 2 or H2SO4, butan 2 or H2SO4. So how does it work? Dehydration. So according to the rule, first we are going to eliminate alcohol. So let me just write my butan 2 back. If I should write my butan 2 back, I should have CH3, CH2, COH. Normally I have a nitrogen there, so I have a nitrogen there. Then I have a CH3. So that makes it a carbon though. All right. So what will be my products? Remember, I lose OH or I lose a base. This is a base, yes. Though it's a bad leaving group, those are for reaction mechanism proper. Okay, so this is a base and the acid spoilate. Yeah, so I remove the base. After eliminating the base, I generate a carbocation. What is the second step? The second step of the reaction is to remove hydrogen from neighboring carbons. So I either remove hydrogen from here or I remove hydrogen from here. All right. Following the SAYTZEFF rule or the SAYTZEFF rule, following the SAYTZEFF rule, the hydrogen is going to be removed from the, according to the SAYTZEFF rule, from the least substituted carbon, or rather, I'm going to get alkenes. Please listen to this. I'm going to get an alkene that has more alkyl group. Now let me explain. If I remove hydrogen from here, according to SAYTZEFF rule, if I remove hydrogen from here, I have two other alkyl groups. Now, but if I remove hydrogen from here, please follow me. If I remove hydrogen from here, I will have just, so if I remove hydrogen from here, I will have now CH2. I will have just one alkyl group. But when I remove from here, so let's assume I remove hydrogen from here and form my double bond here, I still have two alkyl groups. So removing from here makes it the most substituted alkene. Now let me break it down to local language, so the way you can easily understand it. So when performing SAYTZEFF rule, and when two carbons are in competition like this, remove hydrogen from the carbon with less hydrogen. So I can either remove hydrogen from here or remove hydrogen from here, but because I'm obeying SAYTZEFF rule, I will remove hydrogen from this carbon because it has less hydrogen. If it was Hoffman's rule, I will remove hydrogen from the carbon with more hydrogen. So since I remove carbon with the, since I remove hydrogen from the carbon more hydrogen, according to, if I'm obeying the Hoffman's rule, according to the Hoffman's rule, I'm going to produce an alkene that is least substituted. So this alkene will just have one alkyl group, one substituent. But if I remove it from here, the alkene will have two alkyl group. So SAYTZEFF rule or SAYTZEFF rule, remove hydrogen from the carbon with less hydrogen. According to Hoffman's rule, remove hydrogen from the carbon with more hydrogen. So SAYTZEFF rule is, or SAYTZEFF product is usually the most stable product in our today organic chemistry. So what's going to be our product in this reaction? I remove the OH, I remove H from here. Why? Because that carbon is the carbon that is having lesser amount of hydrogen. So this is going to be my product. So I'm going to get both 2 in as the product. Both 2 in as the product. Both 2 in. Now, in this reaction, both 2 in is going to be major products. So for some of us that they can also ask, for this reaction, they might ask you, for this reaction, what is going to be minor product? So what is our minor product for the reaction? So the minor product for this reaction can be, CH3, now CH2. Now I'm going to remove hydrogen from this carbon here. So this is both 1 in. So this is both 1 in. So both 1 in becomes a minor product. a minor, this is major product, this one becomes a minor product. Yes, minor product. But for Hofmann's rule, if I'm obeying Hofmann's rule, or if Hofmann's rule is to be obeyed, this Butuan in the least substituted. When I mean least substituted, that's one alkyl group. Here, that's two alkyl groups. So this the least substituted alkene is going to be the major product. So that's for Hofmann's rule and Zaitsev rule. This is how we use them. So I'm going to apply another reaction. So I'm going to apply another reaction, and I'll just one more reaction on elimination. So you go and try all that by yourself. Try all that yourself. Make sure you can write the structure of the alkanol you're about to dehydrate. So quickly, I'll try one other one, and okay, I'm going to fix this one. So I'm leaving my arrow, showing dehydration. So that's the product. So I'm leaving my arrow. So I want you, okay, I want you to try dehydration, or let's make it let's make it let's make it a little bit complicated. Let's make it okay. So let's say CH3 CH2. Okay, see how more complicated can it be? How more complicated can it be? So let me just try simple ones. So let me go of the video not be to always intimidate you. So this is butanol, or this is one butanol. Okay, this is one butanol. All right. So I think for one butanol, if you check, this carbon has just one adjacent carbon. So what do I mean? So if I remove OH, so let me just show my products. So if I remove CH3, all right, CH2, CH2, okay, that's not one butanol, pardon me, that is one propanol. My bad, that's one propanol. Okay, that's one propanol. So I have one propanol. Okay, this is it. So one propanol. So if I lose OH from here, the adjacent carbon, that's just one adjacent carbon. So I'm going to lose OH from here. So losing OH from here. So then I'll lose one H from here. So I'll create a double bond. So I will still get prop 1 in. So elimination of primary alkanols usually not give us problem. So usually where the problem is elimination of a secondary alkanol, or the dehydration of a secondary alkanol. And please take note, you should be noted that the ease for dehydration is 3-degree alkanols are easily dehydrated compared to 2 degrees compared to 1 degrees. Most, especially when the elimination reaction is following an E1 mechanism, it is always like this. This is the ease for elimination. For dehydration,